In this video, we complete our discussion of intermolecular interactions by talking about what we call dispersion. Dispersion interactions are the weakest type of all of the interactions that we have studied so far, but they play a major role in the life sciences and in chemistry in general. Alright, so the idea is that you can have molecules that don't have a permanent dipole moment, they are not charged, but they can still interact. Okay, so for example, think about two molecules of methane. Okay, C, H. Okay, that's one molecule of methane. And then you can have a different molecule of methane that is nearby. Again, when we look at the charge polarization in that molecule, you can see that there's not a permanent dipole moment. This molecule is not an ion. Okay, so the question is, well, how is this molecule going to be able to interact with another molecule like it? Again, the idea here is that even if these molecules don't have a permanent dipole moment, okay, the electronic clouds are polarizable. Okay, and we say that these molecules have a polarizability. Right, so the idea is that again, the electronic charge in these molecules might fluctuate temporarily, not permanently, but temporarily, so that perhaps in some period of moment in time, all of a sudden there's an excess of negative charge here. That means that there's an excess of positive charge elsewhere in the molecule. Right, so if you actually have this dipole fluctuation, this charge fluctuation to generate this instantaneous dipole, a molecule that might be nearby, okay, might react to this temporary dipole moment to move the electronic charge a little bit towards the center of the molecule, generating a positive right here, and then this allows for electrostatic stabilization and an attractive interaction. Okay, so that's what we called dispersion interactions. They also receive other names. People call them also London type interactions. Okay, and we can also examine how the potential looks like. Okay, and the potential is just going to be proportional. That's the attraction energy is going to be proportional to the product of the polarizabilities of the molecule. Okay, so that would be the polarizability of one molecule, the polarizability of the other molecule, divided over R to the 6. Okay, so here is another example of what we call a van der Waals interaction. Okay, so this kind of finishes our discussion of intermolecular interactions, where we've gone from the strongest type, where you have the attraction between two fully formed ions, which is captured by Coulomb's law, through a series of decreasingly strong or increasingly weaker interactions. Okay, where you have an ion dipole, dipole-dipole, and all the way until you get to dispersion. Now, what is interesting to remember here is what is that controls the attraction. Is this a charge, a dipole, dipole-dipole, polarizability? And it also is important to recognize what is the distance dependence of the attraction. In other words, what is the power of this R that you have in the denominator? Okay, notice that there's actually three types of forces, three types of attractions that have an R to the 6 dependence, and that is interesting because that's what we call van der Waals forces. Okay, notice that the average dipole-dipole interaction in solution is an R to the 6, the dipole-dipole induced interaction is an R to the 6, and the dispersion is also R to the 6. Okay, so this dispersion interaction again plays a major role in the life sciences. Okay, because you can think that whenever you have a hydrophobic chain, okay, so suppose that this is a phospholipid bilayer to mimic a cell membrane. Okay, notice that these hydrophobic chains are apolar, right? They are just aliphatic chains, CH2, 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 occasionally some branches, occasionally some unsaturation. And right there, actually, what you actually have is dispersion interactions between these chains. Okay, that is all dispersion. Now, something that is interesting is that even though one dispersion interaction is very weak, okay, so the type of interaction between this CH2 group and that CH2 is actually quite weak, because you have long chains. Okay, you have those interactions throughout the chains. Okay, and that means that the attraction energy between the hydrophobic tails in the lipid bilayer is actually quite large, because again it's the sum of a large number of individually weak interactions. Okay, so this is how these type of interactions play a role. Now, what is also important, goes often unnoticed, in discussions of dispersion is that dispersion is always present regardless of what the dominant type of interaction is. For example, if you have a dipole-dipole interaction, a textbook dipole-dipole interaction like this one, okay, so most of the attraction is going to be captured by this expression if you actually do it in the gas phase. Okay? But at the same time, what people forget is that the electronic clouds of these molecules are polarizable, right? So there's a polarizability here and a polarizability there. And what that means is that even though the dominant force in this attraction might be dipole-dipole, okay, because this is polarizable and that is polarizable and everything is polarizable, you're always going to have a small contribution due to dispersion. Okay, so every single of these forces is always going to have a contribution due to dispersion. The fact that those electronic clouds can deform temporarily to augment the attraction. Okay.